Hello, everyone. Welcome to the workshop of this RoboDrive challenge. I will leave the time for to Yaru for introducing the opening of this challenge.
Oh, actually, hello. Can you hear me?
Hello, Benoit.
I can try to do it. So I'm Benoit Cotreau. I'm a professor in computer vision at University of Singapore. I'm sorry because I'm in ICRA right now and the Wi-Fi connection is horrible. So I'll do my best to introduce the competition and we'll see how it goes.
Okay, thank you very much.
Welcome to the RoboDrive challenge at ICRA 2024. I'll be leading if I can, the presentation with Yaru Niu and Ling Dong Kong. And so this competition is in Japan at Yokohama. And so the general idea of the competition, if you can move to the next slide. Oh, maybe first we can go to the agenda. So during this talk, we'll first discuss about the competition overview. Then there will be a spotlight talk, and then a track presentation, and finally the award ceremony, followed by concluding remark. By the way, can you hear me well?
Yes,
okay, so as a perfect. Okay, as a competition overview, perceptual task for autonomous driving has evolved tremendously over the last years. So tasks such as bird's eye view detection, segmentation, occupancy, and depth perception are now very well performed by AI systems. But we don't really know how these systems behave in the case of corruption in the data. And so we don't really know how robust they are in such situation. And so this is the objective of this challenge, to see whether AI techniques for scene perception can be robust to corruption. So what we did was to design different sort of corruption to obtain challenging conditions. So these different types of corruption can be from the camera itself. So this is a previous slide. So you can think about corruption in the acquisition of the image, camera failure, or failure in the LiDAR. But there can also be corruption in the visual scene, but also in the data processing and acquisition. So this is the next slide. So this is what we did to change some properties of the images by inducing motion artifact, quantization artifact, introducing change in darkness, brightness, introducing some snow, fog, and also camera crashes and frame loss to the data. And so with that, we designed different corrupted data set, and the objective of the challenge was to estimate different properties of the scene from these data sets. So if we can go to the next slide. Okay, so just give me an overview of the competition organizers. So we are free online today, but we are much more to work on this challenge. So Lingdong and Yahoo worked a lot on that, but there are also all the people that you can now see on the screen. And before to go to the competition overview, let me say just a few words about the codes and also about the sponsor of the event. So the two code base, all right, if you can go back. The two code base that were used to develop the RoboDrive view and Robo3D benchmarks can be found at the following GitHub links. And also one link of interest is the one on the next slide on NM Detection 3D, which is an open source toolbox based on PyTorch towards the next generation platform for general 3D perception. And so this was made by the Shanghai Artificial Intelligence Laboratory. So a last slide before to go on the statistics, to mention the Descartes program, which is a collaborative hybrid AI program developed between France and Singapore. And both Lingdong Kong and myself are part of this program. And you can find more information on the internet link on the right of the screen. So can we go to next slide? So there's one sponsor for this event, which is Huawei. And Wei Qiu is with me at ICRA right now. And on the behalf of all the people who worked on this committee, we would like to thank Huawei for its support for the organization of the event. And now I will let Lingdong present the statistics of the competition.
Okay, I will take from here, and thanks, Benoit, for the introduction. Okay, please move to the next slide. Okay, so there are five tracks in this competition, and we are focusing on 4 different driving perception tasks, including bird's eye view detection, HD map segmentation, semantic occupancy prediction, and depth estimation. So the first 4 tracks are using the camera images as the input, and for track 5, we also include the LiDAR sensors for doing the multimodal bird's eye view detection. Next slide, please. We also have 2 phases. Phase 1 is from January to March. This is for all the teams to do preliminary explorations of the possible solutions in this competition. And for the phase 2, which is from March to April, all the teams must to prepare their final design and solutions and submit to the leaderboard. Okay. Please move on to the
workshop.
slide.
We organize.
Next slide, please. Okay, so these are the key statistics of this competition. We have 140 teams who have filling in our questionnaires and made the registrations. These 140 teams are from 93 different institutes, including the universities and the companies. And these institutes are from 11 countries. And these are the countries the institutes belong to, which are participating in this competition. And so among these 140 teams, we have selected 15 top performing teams. These are the candidates for the winning prize. But this, please pay attention to the this slide, because the order here is not for the ranking. It's just for showing that these are the candidates for our winning prize. Okay, next slide, please. And these are the academia institutes, universities, and research labs, which are top performing teams belong to. Okay, and these are we also have some teams from industry, and these are the top performing teams. These companies are from the autonomous driving related industries. Okay, some of the more detailed statistics of this competition. These are the number of submissions that we received on our evaluation servers. So there are 5 tracks, and we can see that the first track received the most of the submissions for this competition. And this is so the phase 1 received more submissions than phase 2 in general. But the phase 2 is also very challenging. So some of the team didn't participate in this phase. Okay, so but overall, we received nearly 1,000 submissions across these 5 different tracks in this competition. Okay, next slide. So I will introduce the some of the results, key results for each of the track. So first is track 1, which is a robust bird's eye view detection. So in this track, we have a baseline model, which is B waveformer. And the performance of this model is just 22.8. But our winning solutions in this track already achieved a 52.1 NDS scores on the evaluation server, phase 2 of the evaluation server, so which is very impressive. Please move on to the next. Okay, so for track 2, which is HD map segmentation, and this is also the case for the winning solution improves the Beavers models from 15.7 to 48.8 MLU scores. Okay, so and for track 3, which is the semantic occupancy prediction track, so our baseline is around OCC, and it only achieved 8.7 MLU scores on our evaluation set, but our winning solution can achieve like 22.3 MLU scores on this track. And for track 4, because the metric is different, is the error rate of depth estimation. So it's the lower the better. And the baseline model is surround depth. It has 30.4 absolute relative errors for depth estimation, and our winning solution can largely improve these baselines on our evaluation dataset. And finally, it's the multimodal bird's eye view detection track. So the baseline model is BV fusion in this case. So there is a nearly 10% NDS improvements from the baseline model to our winning solution. So these are the some of the key results for each of the track in our competition. Please move on to the next slide. Yeah, so I show some examples for the per corruption improvements from track 1 of this competition. So we have included 18 different corruption types for the camera images. So the first category is about adverse weather conditions and lightning conditions. So we can see that the baseline models, which is shown in the blue bars, can only achieve a just ordinary performance under these different scenarios. But the improvements of the state-of-the-art, the winning solutions can largely enhance the performance under different cases, especially for the frost, snow, and contrast, which this model can achieve nearly 40% NDS improvements over the baseline. Okay, please move to the next slide. So the second category is about sensor and movement disturbances, which are the different kinds of blurs. such as deep focus, blur, gloss blur, motion blur, and zoom blur. And also we included the elastic transform and color quantizations. So for all this case, we can see that our state-of-the-art models can improve the baseline by a very large margin. Okay. So finally, this is the third corruption types, which is related to different kinds of noises and the issues during the data processing, such as the pixelate and JPEG compression. So we can see again that our best models can largely improve upon the baseline models. And for example, for the Gaussian noise, the performance can be improved from 20% to 50 to 70%. Okay, so this is the overview of the key statistics in this competition. And for the next part, we will have our spotlight talk. So
yeah, Wenhao, are you here? Yeah, so Lindong, do you want to introduce Wenhao, or I can go ahead to introduce Wenhao?
Yeah, I will introduce.
Okay.
Please move to the next slide, please.
Yeah.
Right.
Okay, so the title of this talk is Challenges and Future Directions in Safe Autonomous Driving. And the speakers will be Wenhao. Wenhao is an incoming research scientist in the Autonomous Vehicle Research Group at NVIDIA. He graduated from the Safe AI Lab at CMU in 2024. His PhD research focused on safety critical scenario generation, and he is interested in reinforcement learning, deep generative models, and causal discovery. During the PhD study, he was interned at NVIDIA, Amazon, and Bosch Center for Artificial Intelligence. So let's welcome Wenhao for his talk.
Thank you for the introduction. Can I share my screen now?
Yes, I think you can share your screen. Can you try that again?
I'll try it again. Okay, is my screen online?
Yep. Yep.
Okay, cool. Yeah, thanks for the introduction, and thanks for the invitation for me to this competition. It's a really cool competition for autonomous driving. And I know you guys, most of you work on the perception tasks, but I hope that my presentation about the safety in autonomous driving could be inspiring to some of the perception tasks. So let's start. I would like to start from some numbers that reported by the California Department of Motor Vehicle Disengagement Report. So I think it starts from 2019. There are some reports like this. It's basically try to show the miles per disengagement for different autonomous driving companies in California, and we see that as this year goes on, we have better performance on this miles per disengagement, which means these companies achieve better and better performance. They drives longer without human take over. So it means that these companies achieve better safety, maybe. But here, actually, this metric per miles per disengagement is it's not a good metric for the safety. So that's why I want to ask this question here: is this autonomous driving companies, these cars, safe enough for our daily usage? So this is the question. And actually, my previous research mainly focused on this problem, like this critical scenario, or most people call it long tail scenario. So basically, in the real world, we have normal scenarios happen with a very high probability in the real world, but we also have critical scenarios that it's very important, but they have low probability in the real world. So some examples of this, like Cruise and Waymo and Tesla and Uber, even Uber vehicle at very early stage of the autonomous driving industry, they have this very serious crash and collision. All of this can be regarded as these critical scenarios. So basically, if we want to evaluate our autonomous driving algorithms, if we just train and evaluate them on normal scenarios, usually it will lead to some biases because this normal scenario will not tell the boundary or the performance of safety under some extreme cases. But here we also know that the safety critical scenarios are rare and long tail. So the problem is that how can we improve this, like increase the probability of this critical scenario, and then we test our vehicle and even train our vehicle on these critical scenarios to improve the safety. So that's the motivation of this safety evaluation. And I think in this talk, I will focus on this definition of the scenario. I know most of you are more familiar with the perception level scenario, but in this talk, I would say most of the scenario will be the behavior level scenario, which means we only care about the static environment and objects with the ground truth shape and locations. And also we have the initial states of the agents. We also have the behavior of the agents. So basically it's a dynamic and interactive scenario, and we run these all things in simulation with graphical and physical engines. So you can still get the perception, image, and LiDAR information, but these are not manipulated or generated by algorithm. It's just the rendering by the physical engines. And finally, after we run this scenario in the simulation, we can use it for model training and model evaluation. So now the next question is how can we design the scenario to test the extreme test the vehicle under extreme conditions? I think a very common way in recent, or maybe in the last several years, there are a lot of research on this adversarial generation, which is a very common and intuitive way, because we can, if we want to find the failure case and find the vulnerability of the autonomous vehicle, we can just use adversarial attack to run the scenario, run the algorithm in the simulation, and we attack this vehicle, and which will use the attack results to train our model, generating model, and then we generate new critical scenarios and test the vehicle again to see if it can successfully solve this scenario. This is a very intuitive idea. There are a lot of previous works, but here I would like to share some limitation of this type of work. For example, here we usually with this adversarial attack, we don't have a very reasonable boundary of the derivation, so that the scenarios usually derive from human behaviors. So which means the scenario is not realistic. It will never happen in the real world in the simulation. This scenario basically in the simulation, so they will never happen in the real world. And the second thing is this kind of adversarial attack only find the worst cases. So basically, I would say it's too aggressive to only find the worst cases, because sometimes the worst case is not the entire set of the safety critical scenario. The last one is poor adaptivity to evaluate different autonomous vehicles, because this adversarial attack usually focuses on one victim model. If we change the victim model, the failure case will not be the same. So this type of scenarios will not be safety critical for other victims. So these are already the three limitations of this type of work. And I think today, because we have limited time, so I will quickly introduce two of my previous research that focusing on different types of perspectives, different from this adversarial attack. So the first one is retrieval augmented generation, which is a very popular term in large language model. But in this paper, we can use this framework to do scenario generation and to do safety critical scenario generation. And the second one is called causality guided generation, which try to discover some causality behind the scenario and try to use the discover causality as guidance for the generative model to generate new and more effective critical scenarios. Okay, so let's start from the first one about this retrieval augmented generation. So I call it a new perspective of data usage, because in conventional methods, conventional generative models, we usually have a generator to memorize the data set. And then during the generation, we have a condition, then we use the condition as a constraint to input into the generator to generate some scenarios. That's what we call conventional methods. And the retrieval augmented generation is a little different. So here we have two models. First one is called retriever. So the retriever does not memorize the data, basically try to select data according to the condition. So sometimes it's not learning based, it's just some rule based or similarity embedding based methods. We just want to give us some retrieval scenarios that follow the condition. And then we have a bunch of retrieval scenarios. And then we have a generator to combine the information of all these retrieval scenarios. Then we can generate new scenario. So this seems more complex than the previous one, but so why we want to do this? I think here I can give 3 reasons. The first one is with the conventional method, it's really hard to generate unseen scenario because this generator only memorizes the data set. Basically, you are doing distribution estimation, and when you're doing sampling, you basically sample from the distribution. And the second thing is we cannot use new data after training. So if you have some new scenario, interesting scenarios collected from the real world, you need to retrain a model or fine-tune a model with this new data. But with this retrieval augmented generation, you can just put them in the external data and use it during this retrieving process rather than fine-tune this generator. And last one is limited controllability because the generator is not trained by seeing all these conditions. So if we use some condition that has never been seen before, the model will fail. But in this case, just if the retriever can give us reasonable scenarios following the condition, the generated scenario will make sense. So that's the last advantage of using this retrieval augmented generation. And I think this structure of the model will be contain too much details, but basically the intuition behind it is that we want to train, first stage is train an output encoder to extract some latent embedding to represent the behavior level scenario. I know it's maybe for the perception level scenario is more complex in this part, but for behavior level scenario, basically we're dealing with some sequential data, sequential location and heading and velocity. So this part will not take too much time to train or get a very good embedding. And then the next stage, basically we're trying to do an inverse KNN stage, which means if we are given retrieval scenarios, can we reconstruct the chorus scenario? Because in the final usage generation stage, we want to generate a scenario that can follow or combine all the information of its surrounding neighbors. So that's why we call it inverse KNN. So basically the training stage follow this inverse KNN pipeline. And I think here can quickly show some results. And if you are interested in the details, you can check the paper. So basically the results first show that we can use the embedding to query similar scenarios. So if we have a full vehicle scenario at the very beginning, they stop at the intersection and start to move, and then we can find similar scenarios in the data set. But this one is a dissimilar scenario, which means the highest, the farthest sample from this query scenario. So this one is also similar. We have intersection scenario with 2 vehicles, one yielding another, and we find 2 similar scenarios in the database. And this is a very similar scenario. So we can also, as I mentioned, we can use this RAG framework for generating controllable scenario, which means if we give it initial pose and map, we also retrieve some yielding scenarios. Then we can generate yielding scenarios following the same initial position and map. And this is overtaking. And at the end, we talk about the safety critical scenarios. We also want to generate some safety critical or even crash scenarios by using some retrieve crash scenarios. So we can create as much as we can given this different initial map and position and initial pose. Yeah, that's the first perspective I want to share about using this retrieval augmented generation for generating critical scenario. And the second thing is using causality guided generation. So here is a very common real world accident. So we can first, as a human, actually, we can reason about this process, the reason of this crash. And actually here, we can also make a graph to show this process. So if we have this vehicle B, which blocks the view of the vehicle A, we have this collision. But if we remove it, we don't have the collision. So here, we can use a very simple graph structure to represent this scenario by describing the causality, the underlying causality behind this scenario. So, but here, if this scenario is more and more complex, if it involves more vehicles, we can increase the number of nodes, and we can use more edges to represent the cause and effect in this scenario. And so with this formulation, we can actually introduce another more sequential formulation using this causality, which we call it causal reinforcement learning framework. Basically, different from the traditional reinforcement learning framework, we try to learn this factorized causal graph rather than a fully connected dynamic model or transition model. We try to factorize this dynamic model and using the edge to represent the connection and causality behind in the time between the time steps. And this connection can be represented as an adjacency matrix. And the learning process of this model is try to estimate the adjacent matrix and use this use this as a causal graph and mask this transition model. So that's the basic idea behind this causality guided generation. So how do we do this with a generative model? Basically, you're trying to learn the causal graph, estimate the causal graph and the behavior model at the same time by learning a joint, by optimizing these two parts. And I think here is also have some details, but I think this figure is enough to show the general idea. So we still want to do a lot online intervention within a simulation, and we can collect new data, and then we can use different methods to do causal discovery with this collected data, and then we can train a word model and do the planning, model-based planning in this simulation by injecting the causal graph into the word model. As I said before, this is just a factorized masked dynamic model. And then we continue this process to gradually improve the discovery part and the planning part. And then finally, we can discover the underlying causal graph, and we can efficiently generate the crash scenario. And this is an example of the discovered causal graph in a very simple scenario. We just try to reproduce the example in the previous figure or video. It just reproduce this scenario. If we want to have a collision, we generate something like this. If we don't want a collision, if we don't want a collision, it will slow down, and the scenario will make this bus drive slower, and the autonomous vehicle will stop and will not have a collision. So that's a very simple idea to show the simple example to show this idea of causality guided generation. So yeah, I think I don't have too much time, so I will quickly give some conclusion about this critical scenario generation. And so I talked about some methods and what is missing here. I think here are some takeaways. So we still need some metrics of realism for this behavior modeling beyond the distribution similarity, because we want our scenario to be realistic. So we need to use real world data. And also we need this the Wurzel attack, because we need a closed loop simulation with a reactive agents in the critical scenario. This is very important, because if we don't have this downstream task and closed loop simulation, we will not have a realistic and reasonable behavior model, and the scenario will be nonsense. And finally, I think it's the most interesting part I'm interested in now, because we need more semantic reasoning of the safety rather than having collision is the simplest way for risk, but it's not enough. We need some semantic reasoning of it. For example, this absence of unreasonable risk is a ISO standard definition of safety. So it's really widely used in industry area. So, well, how can we integrate this in the generative model? It's very interesting. I think here is the more things we can do with this knowledge, with human knowledge, including the causality, but we can inject more human knowledge into it. And so here, I think some levels of this reasoning of risk, this could be very interesting in different levels. For example, in the natural language level, people are very interested in using large language model for driving recently. There are a lot of papers because this language is easy to understand and aligned with human knowledge. But the problem is that this language description could be very ambiguous and inefficient for communication. But maybe language model, because they are very powerful, so they can understand it, but sometimes it's not precise enough. And in other levels, in the next two levels, like using logic expression and using numerical constraint, although they are accurate and precise, but the problem is that it's hard for a human to understand, and sometimes it's not efficient and cannot be scaled up for the data-driven methods. So we do have a lot of trade-offs here, and I think the more interesting thing I would for me now is that how can we find a good definition of this risk, and to have both precision and understandability. I think generally, as my last slide, it generally is the thing. I think next thing interesting I think we can do is we can do some cause and effect analysis of risk, and then we can define some rigorous and flexible definition of the risk. And finally, maybe we can develop a reasoning model to reduce the risk. I know that currently people are trying to use this machine language model as because they are very powerful, they can use it for reasoning. But still, before we do this reasoning part, do we know what is risk, and how can we give a very rigorous definition of risk? I think it's much more important than solving this risk, because I know that most of papers, they find several examples and solve them, but it's not widely enough. It can maybe not extended to other scenarios. So that's why I think it's more important that you use more important to define the risk. Yep. I hope that it could be inspiring to all of you. So that's all my talk.
Yeah, thank you, Wenhao, for the great inspiring talk. So I don't think we have much time left, but because we have the coffee break afterwards, I think probably we can take 1 or 2 questions. If there are any questions from the audience, from Zoom or from live audience. Yeah. Okay. If no questions, thank you, Wenhao, for the talk. And maybe we can proceed to the next part. Okay, then we'll go to the presentation section from our top performing teams of our challenge. We have 5 tracks in total, and for each track, we'll have 3 presentations. So these 15 presentations will be divided into 2 parts. Between these 2 parts, we'll have a coffee break lasting about 30 minutes. So, okay, then let's go to our first track, robust BEV detection. We have 3 winning teams. Let's congrats to Deep Vision, Ponyville, Autonauts Ltd, and Cyber BEV. So the first team will have a live presentation. I just want to confirm if Deep Vision is here.
Yeah.
Okay, great. Yeah. So I'll let you share your screen.
Okay.
Yeah, and at the same time, I would like to say that so each talk will last about 4 minutes. If it's a live presentation, the talk will be followed by a 2-minute Q&A session. If you have questions, feel free to type your questions in the chat, of course, during the talk. And you can also ask questions after the talk during the Q&A session directly from Zoom. If you are a live audience, I think probably you can go to the Benoit's computer, but I think the best way is to use the Zoom link and ask your questions through Zoom. Okay. Yeah.
Can you see my screen?
Yeah. We can see the screen.
Okay.
Yeah. You can take it from here. Yeah.
Hello, my name is Tao Xu, and I'm glad to share our solution of the track 1 challenge, that is TSMABV. The camera-only 3D perception methods tend to overfit on the training data, which leads to performance degradation when facing out-of-domain data. The challenge requires us to develop an algorithm that can deal with different out-of-domain corruptions, and such as severe weather conditions and sensor failures. And previous works based on the frequency domain perturbations have shown us some examples of frequency domain attack and amplitude phase recombinations. And the perturbation in frequency domain plays a key role in reducing the sensitivities of the model to specific domain data. Frequency domain information loss can bring huge performance degradation in 2D tasks, and people also propose to the amplitude phase recombination method to perform data augmentation to draw the model's attention to structural information and improve its stability under amplitude perturbations. And to tackle the out-of-domain 3D detection problem, we propose a novel training pipeline called TSMA-BV, and we chose solar fusion as our baseline model, which leveraged both long-term and short-term stereo depth potential. And TSMA is the augmentation module we proposed, which consists of the two parts. The first one is aug-FFT, and the second one is a sequence mix augmentation strategy. In addition, we also use model scaling method by increasing the BV feature size. As for the aug-FFT, it is inspired by previous frequency domain analysis works. We proposed 4 augmentation operations in frequency domain. The first 2 operations are doing amplitude clipping on the upper bound and the lower bound, and the last 2 operations are doing specific band amplitude scaling according to the cutoff frequency and predefined hyperparameter delta. And we also use another 2 augmentation operations and avoid any overlap with corruption types in the evaluation data. Thus, we construct a operation bank with 6-unit augmentation operations. And to better facilitate the temporal information, we propose to apply each augmentation chain to a mini-sequence during training. This is to avoid the temporal inconsistency caused by random augmentation between adjacent frames. Each augmentation chain corresponding to the mini-sequence consists of maximized 3 random sampled operations, and we also include no operation augmentation with the portion alpha, and to avoid overfitting on augmented data. And different from augmix, we superimpose the operations in each chain on the input data. And furthermore, we decoupled the mapping between the specific
Hi,
sequence.
Xu. Can I interrupt you? So some of our audience from the Zoom noticed that you have some masks on your screen. Did you notice that? I can also see the masks. Can you remove it? Or oh yeah, that looks great now. Yeah.
Okay.
I think this okay. Go ahead.
It's a Zoom. Furthermore, we decouple the mapping between the specific sequence and augmentation chain to reset the mapping buffer each time when it is full. And these are our main results. And we did ablation studies on the mixed ratio alpha and each module. And the proposed data augmentation module and the sequence mix augmentation strategy plays a key role in improving the model's performance under out-of-domain corruptions. And we also tried augmix and find that it is not appropriate to apply directly to 3D tasks. And in conclusion, we propose TSMA-BV, and which mainly consists of 2 augmentation modules. aug-FFT adapts to 3D perception tasks and enhance the robustness of our model, while the sequence mix augmentation extends aug-FFT to temporal sequences, further improves the OOD performance on corruption data. That's all about our work. Thank you.
Great. Thank you. Now we have 2 minutes QA session. If anyone has any questions, you can raise your questions directly. Yeah, you can unmute yourself.
Hi, can you hear me?
Yeah.
Yeah.
Thanks for your great talk. I have one question related to the second data augmentation you mentioned. So can you share some insights of why, if we make the data augmentation consistent across a frame, it can make the model better? Can you share some insights behind that?
Previously, we have tried simple applied the augmentation to each frame with different with random sampled parameters, and the results turn to bad, and we think that it's cause we use the long-term sequence informations fusion, and we think if the augmentation settings inconsistency due in the long sequence, and the information fusion will pull down the final performance, and it's not good for the robustness of the long-term information fusion 3D perception models.
Oh, okay, thank you.
Okay, thank you, Xu, for your talk.
Thank you.
Thank you. Yeah. Yeah, congrats again, Deep Vision from Hong Kong University of Science and Technology. Yeah, the next team is Ponyville Artonauts. They're from Beihang University, Tsinghua University, and Hebei University of Technology. I will play their recorded talk.
Good afternoon, everyone. Today, I'm thrilled to introduce our solution to RoboDrive Challenge Track 1. First, let me introduce the motivation behind our method. BEV detection system integrated data from multiple sensors to create a consolidated and actionable understanding of road conditions, obstacles, and navigational cues. However, the dynamic nature of driving environment, coupled with the inherent limitation of current detection technologies, poses significant challenges. Our approach, Multi-Wheel Enhancer (MWE), employs a combination of state-of-art technologies and methodologies to ensure high performance and adaptability in real-world driving scenarios. Here's a pipeline of MWE. As you can see in the diagram, we firstly input clean images, which then undergoes random processing through Argmax and debug, resulting in various enhanced images with different effects. These images are then fed into our detection models for training, which is based on the architecture proposed by Radian and use EVA-VIT as a backbone. MWE follow a novel method Radian for camera-only 3D object detection by implementing depth-aware hard negative sampling directly along camera rays. Radinoising creates hard negative samples that are visually indistinguishable from true positives, which force the model to refine its ability to discern depth-related features. For backbone, MWE employs the EVA-VIT large. The EVA2 backbone utilizes an updated transformer architecture and has been extensively trained to reconstruct robust, language-aligned vision features via masked image modeling. This allows EVA-VIT large to excel in extracting high-quality features that are crucial for precise object detection, even under variable environmental conditions. To ensure that MWE performs reliably across varied and unforeseen optional conditions, our approach incorporates two data augmentation strategies, Argmax and debug. Here are some realization of enhanced data. Argmax is designed to enhance model robustness by applying the combination of simple image processing techniques. Here we choose pixel shuffle, random hue, and random saturation in maxing process. Debug, on the other hand, represents a more radical departure from traditional data augmentation techniques. By passing clean image through image-to-image network like CAE, as shown in this page, and EDSR, and introducing random perturbation at various layers, debug generate image differs significantly in appearance from original versions. Then I will talk about the experimental result. Table 1 and Table 2 display the result of our baseline radian and MVE method on 18 corruption tabs of NDS metric. By argmax processing, the average NDS achieved 0.488. Then following the addition of debug enhancement, overall robustness further improved to 0.502. This indicates that both argmax and debug enhancement contribute to improved NDS across dataset. Furthermore, the performance of our method on nuisance validation split is evaluated. As shown in Table 3, compared to BV-former, radian, MVE's data augmentation techniques do not overly impact performance on clean data, preserving the method's detection capabilities on uncropped datasets. At last, I would like to extend a heartfelt thank you to the organizer of RoboDrive Challenge for their incredible support and hard work, and also thank you for listening.
Okay, unfortunately, the team members from Ponyville cannot come to the event, so we won't have the QA session. Let's go to the next presentation. Next presentation will be from the CyberBev BV from Beijing University of Post and Telecommunications. Okay, let's directly go to their talk.
Hello everyone, my name is Yang Bo. It's my pleasure to be here to represent our team CyberBev and share the competition approach. Our model is named Focal Angle 3D. In this work, we design a two-stage model and introduce a new angle encoding method to improve the angle precision. Our model builds upon the string PTR paradigm. It means the original module MLN and a hybrid attention for temporal fusion and deformable attention for spatial fusion are all used in our model to improve the robustness of the detection, particularly in challenging corruption scenarios. On the one hand, we add the first stage mono 3D submodule ahead of the main architecture. On the other hand, we introduced a novel angle encoding module called phase shift coder in Focal Angle 3D decoder module. Firstly, for the mono 3D module, we incorporate a 2D detection network ULX, follow wrap DTR 3D by employing 2D detection task as auxiliary supervision. We enable the backbone network to capture better feature innovatively. Our approach adds more precise depth information into the extracted 2D feature by integrating an intensive depth prediction network, which enhances feature extraction and contributes to more accurate 3D bounding box regression. Specifically, we conduct depth map prediction for the 4 feature maps with different shapes. We adapt one-mount-one convolutions to output depth prediction values for these feature positions. Second, in our competition, we introduced a novel angle encoding method called phase shift encoding. This method utilizes 3 values, which are cosine x, cosine x plus 120 and cosine x plus 240 degree. In contrast to the 2 values used in sine and cosine encoding, phase shift coding provides more angle information. This diversity enables the model to better capture subtle variations and differences in angles. The 3 values are phased at intervals of 120 degrees, providing additional constraints and assistance, making it easier for the model to distinguish differences between different angles. In theory, this phase shift encoding can be adjusted and modified flexibly. By altering the phase difference, the encoding dimension can be changed to adapt to different problems and scenarios. For example, a step can be adjusted to 5 steps, 7 steps, or other odd numbers. This flexibility enhances the versatility and adaptability of phase shift encoding. Since PSC encoding is derivable, we can insert the encoding process directly into the forward structure of the network during training without using encoding. If the approach is adopted, PSC becomes part of the network's forward structure. Experimental results also prove that our method has significant improvement on the model to predict the position, angle, and the speed of the 3D bounding boxes. The first stage mono 3D mainly helps to improve MAVE metrics, while PSC mainly helps to improve MAOE metrics. Okay, that's all. Thank you for watching.
Okay, thank you for the talk. So this is a wrap up for the first track, robust BEV detection. Congrats again to the above 3 winning teams. Now we have 3 great presentations for track 2, robust map segmentation. The 3 winning teams are SafeDrive SSR, Crazy Friday, Samsung. Congrats to the 3 teams. So 2 of the presentations will be live presentations. So please be prepared. The first team, let's welcome the first presenter from SafeDrive SSR from University of Chinese Academy of Sciences and Tsinghua University. SafeDrive SSR, are you here?
Hi, I'm here.
Okay, great. Then you can share your screen and take it from here.
Yeah, okay. Oh, can you see my screen?
Yeah, yeah.
Okay.
Yeah.
Let's start. Good afternoon, everyone. We are the team SafeDrive SSR in track 2. I'm the team leader Xinliang Huang from the University of Chinese Academy of Sciences, and my teammate Yu Tian is from the Tsinghua University. I'm so glad to present our winning solution in the RoboDrive challenge track 2. Okay, in this track, the task is robust map segmentation. This task takes multi-view images as input and generates the corresponding map elements at the BV space. The main goal in this track is to train models on clean data from the new scenes training set, but test on the corrupted data. During inference, the multiple images are corrupted by 18 corruptions, which proves the auto-distribution robustness of models. And our baseline is Beaverse, which is a multitask framework that achieves 3D object detection, map segmentation, and motion prediction simultaneously. In our solution, we only focus on the map segmentation branch and remove the other 2 branches. While Beaverse is capable of fusing historical BV features to facilitate the map segmentation for current frame, We find this approach does not lead to an improvement in the model's robustness. So we remove this temporal fusion and only train and test our models on a single frame. Based on the single frame baseline, we have explored the improvements of the robustness in 4 aspects, including data augmentation, perspective view, auxiliary supervision, trying larger model scale, and post-processing. First, we use pixel shuffle augmentation. Specifically, we first sample a ratio value from a specific range, such as 10% to 40%. Then, using this ratio, a portion of the pixels in the image are randomly selected and spatially shuffled. Such an augmentation leads to better consistency between the augmented image and the original one. We also use some other augmentations, including HSV, cutout, dropout, and augmix to mix all these augmentations. For the perspective view auxiliary supervision, we project the map elements back to the image coordinates and adopt a simple segmentation head on the image features extracted by the backbone to guide the backbone the rich information about the maps. We also adopt depth supervision during the training phase. During the inference, we utilize multi-scale test type augmentation and random flip. For temporal ensemble, we follow this simple idea that the global coordinates of all the map elements do not change with the vehicle. So we transform the results from both previous and future frames to the current frame. Here is our roadmap results. Our baseline uses swing small as the image backbone. The 2 most useful improvements are data augmentations and temporal ensemble, as we can see in the table. And here are some visualized results predicted on the corrupted images in the test set. We can observe that our solution can predict robust map segmentations under many corruptions, such as darkness, Gaussian noise, fog, and motion blur, zoom blur, and snow. That's all of our solution. Thanks a lot for your listening.
Thank you for your presentation. Let's go to the Q&A session. Any questions from the audience?
Hi, can you hear me?
Oh, hi.
Yeah. I do have a question regarding your pipeline. Can you switch to the slide of the pipeline?
Yes.
Yeah, here. As you can see here, first you have a data augmentation, including some really different augmentations such as pixel shuffle or cutout. I wonder when you do the auxiliary supervision, will such kind of data augmentation affect the ground truth, or how do you deal with this?
Oh, during in the auxiliary supervision, the the depth and the segmentation is just it's just a label in the perspective view. So it can be independent between the input images. So generally speaking, this supervision is not has not been affected by the augmentations at the image level.
Oh, I see, I see. So, your data augmentation will not change the labels, right?
Yes, that's my point.
Yeah, I see. I see. Thanks.
Okay, if there are no more questions, let us thank the presenter again.
Okay, thank you.
Thank you very much. Thank you. Then let's welcome our presenter from Crazy Friday from Beijing Institute of Technology and Magvi Technology. Crazy Friday, are you here?
Hello.
Hi. Yeah, you can take it from here. Great. Yeah, we can see your screen, but we cannot hear your voice. Hello? Hello? Hello?
Hello, I can't hear the voice.
Hello, presenter, are you here? Hello? Did you mute yourself? Hello? Can you unmute yourself?
Hello.
Hello? We can hear you for like a second. Hello? Can you type something in the chat if you met some issues? Probably we can switch the presenting order a little bit. If you can hear us, could you please type in the chat? Okay, yeah. I guess we'll come back to this presenter later. Yeah. If you fix the problem, please let us know in the chat. Okay. Okay. We'll proceed to the next presentation for now. Yeah. Okay. The third presentation for track 2 would be Samsung team from Samsung Research and Development Institute, China, Beijing, and the University of Sydney.
Hi, everyone.
I am Hao Xiaoshui. I am from Samsung Research Center. Today, it's my great honor to be here share our technical report for 2024 RoboDrive Challenge Robust Map Segmentation Track. Let's introduce the first part, background. The robust map segmentation track focuses on the segmentation of complex driving scene elements in BEV maps under varied driving conditions. Semantic map segmentation provides abundant and precise static environmental information crucial for autonomous driving systems planning and navigation. While current methods excel in ideal circumstances, e.g., clear daytime conditions and fully functional sensors, their resilience to real-world challenges like adverse weather and sensor failures remains unclear, raising concerns about system safety. In this paper, we explored several methods to improve the robustness of the map segmentation task. The details are as follows. Firstly, robustness analysis of utilizing temporal information. Secondly, robustness analysis of utilizing different backbones. Finally, data augmentation to boost corruption robustness. Based on the evaluation results, we draw several important findings including the temporal fusion module is effective in improving the robustness of the map segmentation model. A strong backbone is effective for improving the corruption robustness. Some data augmentation methods are effective in improving the robustness of map segmentation models. These novel findings allowed us to achieve promising results in the 2024 RoboDrive Challenge Robust Map Segmentation Track. We first establish a baseline of semantic map segmentation based on the state-of-the-art BEverse model. In this paper, we explored several methods to improve the robustness of the baseline map segmentation model. In this setting, we comprehensively investigate several backbones and show the results in tab 1. We construct 3 versions of BEverse, namely BEverse Tiny, BEverse Small, and BEverse Base. Specifically, we use Swin Tiny, Swin Small, and Swin Base Transformer as the backbone, respectively. The experimental results demonstrate that the BEverse base, using a Swin Base Transformer backbone, has significantly improved the robustness. This shows the effectiveness of the strong backbone in improving the corruption robustness of the semantic map segmentation model. We investigate the impact of utilizing temporal information module on the robustness of semantic map segmentation and show the results in tab 2. The experimental results demonstrate that the temporal fusion module can significantly improve the robustness. It can be observed that BEverse base with temporal fusion achieves 2.4 absolute gains on the MIOU metric on the Phase 1 test set. This shows the effectiveness of the temporal fusion module in improving the corruption robustness of the semantic map segmentation model. In this setting, we investigate the effect of various data augmentation techniques on the robustness of map segmentation models. Specifically, we use several image data augmentation methods, i.e. grid mask, random hue, random saturation, random swap channels, and random value. We choose BEverse Tiny, W/temporal, as the base model, and the results are shown in tab 3. It can be seen that image data augmentation methods moderately improve the model's robustness performance. This shows the effectiveness of the image augmentation methods in improving the corruption robustness of the map segmentation model. Tab 5 lists the augmentation methods and their descriptions and ranges we use to augment data. Figure 2. Examples of augmentation methods used in our method. For the main experiments, we use BEverse Tiny with the temporal module as the base model and use some data augmentation. Tab 4 shows the overall performance of our method. In a nutshell, our method shows significant superiority over other methods, indicating the benefit of the temporal module and data augmentations. Note that due to limited time, we did not conduct related experiments on BEverse base. We believe that experimenting with strong backbone models will further improve robustness performance. By conducting large-scale experiments, we draw some important findings, as summarized below. By analyzing the impact of different configuration options on corruption robustness, we find that the recipes for a robust map segmentation model may include utilizing a temporal fusion module and strong backbone, e.g., Swin Base Transformer. Some data augmentation methods are effective in improve the robustness of map segmentation models. Nonetheless, Further investigation into more advanced augmentation methods is warranted for future research. Thanks for attention.
Okay, great. This will conclude the presentations from our second track, robust map segmentation. Congrats again to the above three teams. To the second team, Crazy Friday, if you want to present and fix your issues, just let us know. Okay.
Hello, can you hear me?
Yeah, I can hear you now. Yeah.
Oh, okay.
Okay, great. Yeah, please take it from here. Yeah.
Okay, let me begin. Hello, this is the presentation for the solution of the team Crazy Friday. Let's begin with the introduction. A common three-dimension detection framework first use a backbone to extract features from surrounding images, and then construct by bird-eye view features through geometric transformations and decode the corresponding text through by features. The specific text decoders had mainly focus on the specific tax of refinement, receiving features from the by feature. It is constructed by the geometry transformations of the image features extracted by the backbone. Ultimately, is the backbone process the image primarily to reconstruct the features under the corruption. Therefore, for various camera corruption problems, a powerful and robust backbone may reconstruct clean features from visible and deformed image through strong knowledge barriers. Some approach for training using such as mixed image modeling (MRI) method may help to alleviate corruption problems. And for the problem of camera crash and frame loss, the spatial temporal method may effectively alleviate them because the previous image can complete the missing image and short-term camera crash. So this is our framework's approach. First, the image feature is extracted from the surrounding image by the backbone. And for each timestamps, a geometry transformer uses multi-view features cover the entire surroundings to create the by feature. Next, we add in the by feature from past timestamps to the present frame using non-equal motion. And finally, the map decoders, whereas a simple MLP multi-layer perceptrons are employed for the map segment constructions. And this is the implement of our frameworks. We analyze different backbones, including swing and EVA, as shown in the right table. Scaling up vision ability demonstrates improved performance by increasing the number of parameters and data. We think larger parameters and pre-trained data for the backbone may improve robustness of feature extraction under various corruptions. And we also investigate the effect of training epochs as shown figure in the right. The best performance occur in the epoch 5. We hypothesize that the model may overfit the dataset due to the optimizer focusing on the specific refinement strategy. This refinement may affect the robustness under various and challenging conditions while improving performance on specific data sets. So this is our solution. We instruct multi-view architecture incorporating temporal information combined with a scaling up and the training strategy to improve the robustness on the various corruption scenes. And this is my presentation. Thank you.
Yeah, thank you for the talk. Any questions from the audience?
Can you hear me?
Yes.
I noticed that the main contribution of your work is to use a larger and stronger feature extractor backbone. Is that correct?
Yes, this is one main contribution, and we also take some like temporal and special elegant method.
I see. So do you observe there's a large increase in the latency of the model when you switch to a model with a larger size?
Sorry, can you repeat your questions?
I mean, so do you notice there is a large increase in the time consuming of the backbone when you increase the size?
Yes. But sorry, I don't test the time consuming such as the frame per second.
I see. Thank you.
Okay.
Okay, if there are no more questions, I guess we'll conclude the presentations from track 2.
Hi.
Okay, then we'll have 3 fantastic presentations for track 3, robust occupancy prediction. The 3 winning teams are APAC Blue, HM Unilab, View Former. Let's congrats to the 3 winning teams. Okay, we'll first welcome the presenter from APAC Blue, from Beijing APAC Blue Technology and Beihang University. So this is a live presentation. APAC Blue, are you here?
Can you hear me?
Yeah, we can hear you. Okay, great.
Okay, hello everyone. I'm here to report our solution of track 3 in RoboDrive challenge. Our team is APAC Blue, and I'm Zhang Bingyang. Firstly, we will give a brief introduction of this challenge. The task of this challenge is to probe the out-of-distribution robustness of state-of-the-art autonomous driving perception models. And the evaluation method is mean IOU. The following pictures are some example samples of this challenge. The first section is our network architecture part. Our method is based on surround occupancy. It contains 4 modules. The convolution module, which extracts 2D features. The transformer module, which map 2D features to 3D voxel features. And the 3D convolution module, which create prediction occupancy labels, and the optimization module, which with effective loss and training method. And
hi, actually, I think you are not switching your slides. I'm not pretty sure if you're, I'm not pretty sure if this is a problem for everyone, but I cannot see you're switching your slides. You're sticking to the first slide.
This?
I cannot see that. It's
see
still on the first one. It's still on the first slide.
And this?
Nothing changed.
Okay, sorry.
Can you share it again? No problem. Take your time. Can you share it again? Oh, yeah. Now it works. You're switching to the second.
Okay.
Yeah. Okay, great. Yeah.
Yeah, this is the network architecture. Yes, and we will go to the two section is our approach. We mostly think that two aspects of improving performance. One is that discovering network architectures with stronger performance in the evaluation datasets. The other one is enhancing the module's generalization performance on difficult samples like test sets. We have led many experiments on the challenge. For example, like backbone loss optimization and other attempts. And the most significant method to enhance model performance is our ensemble strategy. We improve the performance of test set by integrating models that training from different network structure and different training strategies. And finally, this is our results and ablation study. This table shows that our model A and model B show our loss optimization and compared with baseline. And model C to E compared different backbones and voxel size parameters. And model F to H show our ensemble strategies results. And finally, I think we have not shown our totally details because the limited time and my limited English skills. So we release our source code in this GitHub link, and welcome to follow our project and discuss more in the future. Thank you.
Great, thank you for the presentation. Any questions from the audience?
Can you hear me?
Yeah,
yes.
yeah, okay.
So first, thanks, Bingyang, for the presentation and for releasing the source code. I have a question for this table here. So you mentioned that you are using the ensemble strategies to combine different results. So how do you do that?
We integrate our model with different training strategy like A and B, and different network structure like C, D, and E.
So after training them, how do you combine their results together?
Let me.
So do you choose the best results for each of the options and add them together?
Yeah, every model has equal weight, but if a class have two or more equal numbers, then the high MLU score models will
be used for the final result.
Will be used in the final submission.
Okay, thank you very much.
Thank you.
Any more questions? Okay, thank Lindong for the question, and thank Bingyang for the great presentation. Okay.
Thank you.
Yeah, great. Okay, then let's take a look at the winning solution from team HM.Unilab from Haomo.ai.
Everyone, my name is Yu Bo Tian. And I'm honored to be here representing Haomo.ai to introduce our solution at the RoboDrive Challenge Track 3, Robust Occupancy Prediction. Haomo.ai leverages advanced AI to pursue zero accidents, eliminate congestions, and ensure efficient logistics. In this competition, our occupancy prediction solution demonstrated decent performance, particularly in handling extreme scenarios, boosting both accuracy and robustness. Today, I'll briefly outline the innovative approaches and key technologies behind our solution. In the field of autonomous driving, it is crucial to ensure the accuracy and reliability of perception systems under various environmental conditions, as well as potential sensor failures, particularly in the area of occupancy prediction. Despite employing advanced BEV displays and LiDAR sensing technologies, we still face significant challenges when dealing with such kind of scenarios. We are deeply grateful to the organizers for providing this platform, which not only allow us to demonstrate our model's performance under real-world conditions, but also helps advance the entire industry in the field of occupancy prediction. In this project, all the corruptions and failures are modeled into a function. This function processes input images to generate various distorted scenarios within the test datasets. By adopting this approach, we are able to assess the model's robustness and adaptability to complex visual conditions in the real-world settings. In our project, we chose to keep using the surround OCC model structure because it has proven to work well in understanding complex environments. We focus on improving the model's performance by introducing new types of loss function and training methods. We tried using VOVNet99 as the backbone of our model. It includes two key techniques, one-shot aggregation and squeeze and excitation. So one-shot aggregation helps to merge features from different stages, which uses the available information more effectively. Squeeze and excitation focuses more on important features, making it better at predicting what happens in complex traffic scenes. We also used a new loss function called Lovat Softmax, designed for tasks where we need to classify into multiple categories. It helps to optimize the model based on the mean IOU, a key performance metric, by making the calculation smoother. This integration has helped to improve our performance measures. Lastly, we explored two different strategies to manage how different loss functions affect each other: loss normalization and uncertainty loss. Loss normalization makes the loss value more uniform, and uncertainty loss lets the module learn and adjust the importance of each function automatically during training, leading to more precise results. Although image-level data augmentation is not allowed in this competition, we still believe that feature-level data engineering is a direct and effective solution. Moving forward, we plan to explore how feature-level data enhancement can optimize PV and BEV features, including studying how image distortions affect them. Additionally, we intend to use masked autoencoder technology to restore and enhance BEV features, further improve the model's accuracy and adaptability. We will also consider more design innovations in our model architecture to continuously push the boundaries of our solution. That's the end of our presentation. Thank you for listening.
Okay, then we'll come to the last presentation of track 3, the solution presentation of Team Viewformer from UIC.
First of all, we're very honored to present our work here, which is Viewformer enhanced the top-ranking solution in robust occupancy prediction. Our solution is based on Viewformer, a robust spatial temporal modeling method, featuring view attention for spatial interaction and multi-frame streaming temporal attention for temporal interaction. We briefly introduce the view attention here. The projection-first method, like BEVFormer, uses deformable attention to aggregate image features. Limited by sensor distribution, a large number of Vox query can only capture features from one camera. While our learning-first view attention learns view-guided 3D points, aggregates multi-view features more adaptively. This module provides a solid foundation for us to construct robust 3D features. For more details, please refer to the paper of VFormer. To further leverage offline future data, which is allowed by the challenge, we propose a reverse video playback mechanism. Let's first review the online video temporal interaction method. On this BV picture, the car is moving forward, and a tree is in the rear area of the car. The corresponding Vox query in our online framework can consistently retrieve hysteric features of the tree from the memory queue. On the contrary, as illustrated in this picture, in case that the tree appears in front of the car, which means it is newly observed. As a result, the Vox query actually gains no benefit from temporal interaction. This figure roughly shows the perception accuracy of different areas around the ego vehicle. Darker colors represent higher accuracy. For the front and rear area, we find the accuracy gap can be up to 3%, and if the video is reversed, we yield opposite result. Based on such observation, we propose the reverse video playback method by simply playing the video backwards without modifying our online framework. Then we just combine the inference outputs of the normal video playback and the reverse video playback to produce the final predictions. A tip is that if you fine-tune the model with the reversed video, the accuracy can be a little higher. At last, we showed the ablation study of our adopted methods and techniques on the validation dataset. The baseline is the ViewFormer framework. Depth supervision for image backbone, like BV depth, increases performance. Our proposed reverse video playback approach also effectively brings accuracy improvements. Moreover, we employ spatial and temporal test time augmentation, such as image flipping. For model scaling up, we use a larger image backbone, a higher input resolution, and an expanded Vox resolution. Please refer to our technical report for more details. Thanks for watching.
Okay, congrats again to the above three winning teams of track 3, robust occupancy prediction. And this also a wrap up of our first part of the winning team presentations. Now we will have a coffee break lasting about 20 minutes. Then we will come back at 3 p.m. So don't forget to come back. We will have our second part of the winning team presentations and 2 spotlight talks, and also importantly the award ceremony. Okay, great. Yeah, we'll see you in 20 minutes. All right, everyone. Welcome back. Now we will have our second part of track presentation. We have 3 winning teams for track 4, our robust depth estimation. Congrats to the following teams: BUA Trans, HITAIIA, and CUSTZS. So from these 3 teams, we'll have 1 team doing their live presentation. So BUA Trans, are you here?
Yes.
Your voice can you say it again?
Can
Okay,
you hear
great.
me?
Yeah,
Oh.
yeah, we can hear you. Just a reminder, for the live presentation, it will last about 4 minutes, and afterwards we'll have a Q&A session, lasting about 2 minutes. You can raise your questions, in the Zoom. Okay.
Okay. Can you see my screen?
Yes, yes.
Oh, okay. Good afternoon. I'm Wang Ziyan from Beihang University, and today I'm excited to discuss our research in the field of depth estimation. And depth estimation is critical in applications like autonomous driving, 3D reconstruction, and robotics. Ensuring robust depth estimation in bad weather conditions is essential for vehicle safety, especially in rain and fog. Currently, models struggle with complex and changeable real-world scenarios, particularly under poor visibility. We aim to develop perceptions models with out-of-distribution robustness. Our approach instead of 3 main components: a multi-branch network, a level feature fusion model guided by the input embedding vector, and data augmentations technical like cut flip and argmax. We designed a 2-branch system to extract image features. The dyno branch capture high-level semantic information, while the ResNet branch identified edge features. Our feature fusions module used SE blocks for attention-based feature integrations. Additionally, we use a simple ResNet to encode an embedding vector, which is used to capture noise for feature fusions. We apply argmix to generate images, and I use KR loss to improve the depth consistency across different enhanced depth maps. We use a 3-phase training process. First, SFM pre-training. Next, training with the dyno branch using LiDAR data. And final, semi-supervised learning with augmented data. In ablation study, each module contributes to robust depth estimations. In comparative study, the modules we use outperforms general methods. And this is the evaluations of our model in corruptions. It is shown that our model achieved high accuracy in the majority of corruption scenarios. But it's also to need to be proved on the contrast, motion blur, force, and fog corruptions. This slide shows our depth estimation result for surrounding views in brightness. We select some example to show the robustness of our model. And you can see our model could distinguish relative depth estimation relationship between different objects. And this case show that our model maintained the schedule consistency of the objects. And this case show that our module estimates depth by effectively reducing noise. In summary, our model shows promise for robust depth estimation in out-of-distribution scenarios. Thank you for listening.
Thank you, Zian, for your great talk. Any questions from the audience?
I have a question. Can you hear me?
Yes.
Okay, so you mentioned that your framework is multi-branch. So this is during the training, but during the inference, how many branches will you use for generating the depth estimation?
Yeah, we use both two branch for training and evaluation because we think nano branch can better catch the high level future, and the ResNet can better to catch the shallow future. Yeah.
Okay, but if you use two branches, then the inference time will be increased from using just a single branch, right?
Yeah. Yeah.
So have you tested the time consumptions of the single branch and the multi-branch versions of your framework?
Sorry, we have not do that, but we think the ResNet parameters is not large and it will not need
It will not be a
time.
big problem, you mean? Okay, so I understand your point, and if you can add some results in the report, then then you will be better because the inference time is also very important for depth estimation.
Yeah. Thank you for your.
Okay, thank you very much for your presentation.
Okay, thank you, Zia, for your presentation. We'll go to the next winning team. Now we'll dive into the solution presentation of Team HITAIIA from Harbin Institute of Technology.
Hello, everyone. We are Team HITAIIA. We participated in the ICRA 2024 RoboDrive Challenge Track 4 and achieved excellent results. Today, I will introduce our technical solution. First, let's review Track 4 of this competition. The goal of this challenge was to enhancing the robustness of depth estimation models in adverse scenarios. We can train the model exclusively on the clean Nussines dataset. In addition, the use of deep learning-based denoising models and foundation models was restricted. 18 types of corruption across 3 categories are considered: weather and lighting, such as snow and fog, sensors and movement, such as motion blur and color quantization, and data and processing, such as Gaussian noise and ISO noise. For this challenge, we adopted a supervised learning approach to train our model, DNOSD. We use LiDAR data to calculate C-log loss as the supervisory signal. To enhance the robustness of our model, we employed data augmentation using AugustMix. The principle of AugustMix is to enhance model robustness by adding random data augmentation chains to images and using the Jensen-Shannon divergence between the augmented and original images as part of the loss function. This approach ensures the model learns the same depth of information from augmented images as it does from clean images. We also incorporated a smooth loss to ensure depth continuity in our estimations. Our model architecture is illustrated in the diagram. We utilized the DynOv2 encoder, which pre-trained on ImageNet, and employed DPT for feature fusion and decoding. Finally, we used the depth head to obtain surround view depth maps. We incorporate cross-attention between adjacent viewpoints, which is more suitable for the surround view depth estimation task. As test pipeline preprocessing, we first use a robust wavelet-based estimator to determine the standard deviation of Gaussian noise as a preprocessing step. Next, we perform non-local means denoising. Then, we separate each channel, apply histogram equalization individually to each channel, and finally merge them back together. The pre-processed images will feed to our DNO-SD model for inference to obtain the depth maps. Empirical results demonstrate the effectiveness of our approach in enhancing model robustness. Compared to other participants, we achieved first place in 7 evaluation metrics. Furthermore, we conducted a lot of ablation studies. The studies confirmed that image denoising, image equalization, and cross-attention contribute to improved performance on the test set. Finally, we would like to express our gratitude to the ICRA organizers for recognizing our efforts. If you have any questions, please feel free to ask.
Yeah, so I noticed in this video, they offer a QA session. I'm not pretty sure if the presenter is here. If you're here, you can unmute yourself so that audience can ask questions maybe. If not,
Oh, can you hear me?
oh, great.
Oh.
Great to see you. Any questions from the audience?
Can you hear me?
Yes.
Can Yaru please turn the video to the first slide? Maybe
First
not
slide.
first, maybe somewhere in the middle, maybe, and show the methods pipeline.
This
Yeah,
one?
this one.
Or okay, great.
Yeah, because I noticed that there is another team which also use a Dino backbone to extract the robust features. And for their team, they froze the Dino backbone to extract the feature. But for your methods, it seems that you are trying to fine-tuning the Dino backbone. Am I correct?
Can you hear me? Oh, yeah, yes.
So do you observe that will there be any influence if we froze the Dino backbone or fine-tuning it? Because I remember that Dino V2 backbone is already a very robust backbone for depth estimation task.
We use Deno V2 because Deno V2 is an encoder that can exact robust image features, but yes, yes.
So do you try to froze the Dino for to do some ablation experiments?
I'm sorry because we didn't do such experiments. We will do these experiments in future.
Okay. Thank you so much for your answering.
Oh, thank you.
Any more questions? Okay, if no more questions, let's thank the team HITAIIA. Thank you for the discussion and presentation. Yeah. So the third So the third team of track 4, robust depth estimation, is CUSTZS from Zhongshan Institute, Changchun University of Science and Technology. Let's enjoy their solution presentation.
Dear leaders, experts, and judges, hello everyone. I am Wang Yuba from Changchun University of Science and Technology in China. It is an honor to present to you the research methodology titled Basic Methods and Related Experiments to Enhance the Robustness of Depth Estimation Models at this RoboDepth 2000 and 24 presentation. Our main task is to replace depth estimation models on established benchmarks. After conducting experiments on various models such as K-depth, zero-depth, etc., in the end, we found that the monovit model based on convolution combined with long-distance information performed the best. We also trained the model using two benchmark training methods. Although it was not submitted to the test server in the pre-training method, it performed better in the evaluation of the raw data. At the same time, monovit was also validated as the most effective solution in resisting data interference in last year's competition. We were fortunate to have found it within 3 submissions. During testing, we employed Restormer to handle the test data. We did not train a new denoising model and only utilized the 4 pre-trained models provided by the official team. Each model exhibited significant optimization for the corresponding noise type. For untrained noise, it had a minimal effect on data with similar noise types, such as zoom blur or snow. However, it was ineffective for several test sequences unaffected by noise, such as brightness, dark, fog, frost, and others. The following are several categories where Restorer performed well in the test set. But we did not achieve the desired effect in processing Gaussian-like noise, which we believe may be due to the smaller size of this year's test data. The following are our experimental visualization results in the second stage of the test set, mainly including categories that Restorer cannot optimize. The data with poor estimation performance in these categories are those with large occlusion surfaces, such as fog and frost sequences. We believe that using temporal estimation methods may perform better than single-shot estimation in these sequences. Concerning the loss function, we continue to employ the loss function from the benchmark method, which did not yield superior performance compared to the benchmark method on the original test data. We also experimented with CVT attention and observed that incorporating it into the MFIT layer of image vectors accelerated training. In general, our approach is still in its early stages of exploration. There is still much work ahead of us, and we will persist in this effort following the release of subsequent test data. Thank you for your attention.
Okay, great. This will conclude our presentations for track 4. I'm wondering if the presenters happen to be here. You can just unmute yourself or let us know in the chat. So, okay. If no, we'll go to our final track, robust multimodal BEV detection. The 3 winning teams are HITSE RoboDrive, Ponyville Autonauts Ltd, and SafeDrive Pro Max. Congrats to the above 3 winning teams. So we'll have one live presentation from HITSE RoboDrive, from Harbin Institute of Technology, Guangdong University of Technology, HKUST Guangzhou, and University of Queensland. Are you here?
Can you hear me?
Yeah,
Can
we
you
can
hear
hear
me?
you.
Okay.
Yeah, you can
I'll
take
share
it
the
from here.
screen.
Yeah, great.
Can you see the screen?
Yeah.
Okay.
Yeah.
Okay, I'll begin. Good afternoon. Today we are glad to be here for this presentation. Our team has developed a novel approach called robust alignment in multimodal 3D object detection. This presentation will cover the challenges we faced, the methods we employed, and the promising results we achieved. As we all know that the failure of vehicle-mounted camera and LiDAR sensors is inevitable in practice, resulting in incomplete data. Existing LiDAR camera fusion methods lack sufficient robustness in these scenarios. This is also the challenge we face. Our method contains two stages. The first stage is the pre-processing stage. Our simulation strategy involves two scenarios to simulate. Damage to one perspective of the camera results in the failure of obtaining images, and malfunction of LiDAR sensor, which leads to sparse cloud point cloud scans. For one thing, we simulate the malfunction of a certain camera of camera clusters by discarding one image. For another, downsampling is applied to corresponding point cloud to mimic two levels of data missing. The second stage is a network. It consists of 4 parts. For the image feature extractor, the image inputs first pass a backbone, which can be swing or resonate, and an image neck, such as FPN, to get image features. Then the depth prior, which is generated from the point cloud projection, is applied to supervise the transformation from image features to image BEV features. As to the point cloud encoder, we first get the point cloud features, and then we pass them through a point cloud backbone, WorksNet, and a point cloud neck, second FPN, to get point cloud BEV features. Then we combine these two types of BEV features in multi-module fusion module to get fused BEV features. Finally, we pass it through the BEV encoder, and the rest parts is similar to the method detecting as labeling. We conducted ablation studies regarding 3 factors. As to the version 1, 40% means we just apply simulation strategy for only 40% of the overall data set, while for version 2 to 5, we apply the strategy to the overall data set. 1/5 means we downsampling the point cloud with the ratio of 1/5, while 1/10 means we downsampling the point cloud with the ratio of 1/10. Mask means we randomly discard one image. For the best performing version 5, we switch to a larger camera backbone, and we apply the simulation strategy of 1/10 and mask. And we appropriately extend the training schedules to 30 epochs. This ensures that the model can adequately fit the corruption data without overfitting, achieving the highest NDS among all the versions. As to the comparison against LiDAR camera fusion methods, compared to the baseline BEV fusion provided by competition organizers, our model has achieved a 7-point improvement in NDS and a 10-point improvement in MAP. Due to the characteristic of point clouds be denser near the sensor and sparser at a distance, targets that are far away are often difficult to detect due to the sparsity of the point clouds. Additionally, in dense distributed region, the point cloud of interference between targets is quite severe. From the first group, we see that a bus is located far away from the LiDAR sensor. Our method can detect it, while other methods fail to detect it. For the second group, we see in the case of dense distributed region, our method accurately predicts the bounding boxes, while other methods either fail to detect it, for example, the B-wave fusion, or suffer from mutual interference, for example, the deep interaction and the DAL. That's all for our presentation. Thanks for listening.
Okay, great. Thank you, Dongyi, for your great presentation. Any questions from the audience?
I have a question. Can you hear me?
Yes.
Okay. First, thanks, Dongyi, for the presentation. Can you go back to the slide for the point cloud downsampling?
You mean this one?
Yes. So
Okay.
you mentioned that you are using a uniform downsampling strategies to create a more sparser point cloud, right?
Yes.
So I wonder, did you try just remove the points from the point clouds at certain like angles, like the
Yes,
front
for
view
this,
or the back
okay,
view?
okay. For this question, we haven't noticed that the situation of some frames losing of point cloud. It is until the last several days we noticed that the point cloud could be missing for some frames. And for
Yes.
the camera images, it also will cause the missing of several images, but we just discard one. So if we apply the strategies that to simulate the multiple frames losing of point cloud or multiple corruption of images, we think our scores can be higher. But unfortunately, we haven't applied the strategy you mentioned.
Okay. I have another question. So because you're creating a very strong data augmentations during the training, like just directly black out certain camera views or create a sparser point cloud. So during the training, have you observed some issues for the loss optimizations?
Can you repeat your questions?
So because you are using a very strong data augmentations during the training,
yes.
so the loss might be not that stable. It might vary between each iteration.
Are you talking about the loss?
Yeah, the loss.
Yes, the loss is higher than the common methods. Than the common methods. For example, for the DAL and B-wave fusion, the loss will finally decrease to 1.4 or 1.5. But for our methods, after we applying our simulation strategies, the the loss finally will come to 2.2 or 2.1, and it is hard to decrease the loss.
Okay. Thank you very much for your answers.
Okay, thank you.
Okay. Thank you for the discussions. Okay, our second winning team of the multimodal BEV detection track is Ponyville Artonauts from Beihang University, Tsinghua University, and Hefei University of Technology. Now we'll dive into the details of the solution.
Hello everyone, let me introduce the work of our team in the RoboDrive challenge, Track 5 Robust Multimodal BV Detection. In the Track 5, we elaborate on the practical application and a demonstration of cross-modal transformer CMT for the RoboDrive challenge. Only little work has been done to develop robust 3D object detection algorithms to address sensor failures. MBV simulated camera sensor failures by masking the camera feature and then reconstructing that camera feature, but lacked research on LiDAR sensor failures. Although CMT was not developed to handle sensor failures, it was found that CMT still has better robustness when missing camera sensors or LiDAR sensors. We believe that the robustness is mainly due to its designed mask training strategy. That is, randomly masking the image or point cloud during the training process. So after comparisons among multiple baselines, we directly followed CMT to tackle this task for its excellent robust performance. Here's the pipeline. Let's talk about how CMT is built. It has a part called the coordinate encoding module, which is used to encode the 3D position information into multimodal tokens. Inspired by pattern, for each image, CMT encodes a set of points in camera frustum space to perform the coordinate encoding. It can be expressed by the following formula. And for the C4 point clouds, the point set P can be sampled along the z-axis, and then get the formula of position-guided query generator and decoder. It is worth mentioning that CMT uses masked model training to make the model more robust. Even if LiDAR is damaged, it can still achieve similar performance compared to the SOTA vision-based 3D detectors. In the experiment, we compared the performance of CMT to the baseline in track 5, where -F denotes the performance of the model under the nuisance validation set for sensor failures provided in track 5. The detailed results are shown in the figure. Well, firstly, it can be observed that CMT outperforms BV Fusion both in terms of clean performance and perceived performance under sensor failures. Secondly, it can be seen that the performance degradation of CMT under sensor failures is much lower than BV Fusion. CMT degraded by 33.88% on NDS, while BV Fusion degraded by 45.24%. In conclusion, CMT shows its great performance compared to other baselines. Thank you for listening.
Okay, congrats again to the Ponyville Autonauts team. Now we'll have our last presentation from the winning team. Safe Drive Pro Max from Tsinghua University. Let's take a look at their talk.
Hi everyone. It's my pleasure to participate in the workshop of the RoboDrive challenge. We are the Safe Drive Pro Max team from Tsinghua University. The team leader is Yang Xiao, and the team member are Chen Hai and Wang Lizhong. I am Chen Hai, and represent our team to report the math we used in track 5. First, we show the results we achieved, and we are honored that our method was ranked first on the leaderboard. Before designing the method, we observed the test data. We found that the camera sensor randomly discard a certain camera view based on the scene token. And secondly, the point cloud obtained by the LiDAR sensor is very sparse. Therefore, for this case, we designed our mask that is against the sensor failure. ASF utilizes self-supervised masks to reconstruct image features when facing camera sensor failures. We follow the design of MBV by randomly masking a certain image feature, then initializing the masked image feature based on the overlapping region of the camera waypoints at the spatial queue. Stacking 6 layers of a transformer decoder to reconstruct the image feature. In addition, we also propose the image feature enhancement LiDAR feature module designed to allow the negative impact of LiDAR sensor failure. Specifically, ICRA projects the point cloud onto the image coordinate system and takes all the features of pixel on the image corresponding to the point cloud to enhance the LiDAR features. For efficiency, ICRA takes out the features of only m pixels around the reference points to enhance the LiDAR features. The experimental results show that ASF sacrifices some of the clean performance to improve robustness, but is able to get security in case of sensor failure. And the visualization also shows that ASF is able to achieve less misdetection and accurate perception. My report ends here. Thanks for listening.
Okay, great. Any chances the team members here? Okay, if not, this will conclude all the presentations of track 5 robust multimodal BEV detection and also the presentations of all the track presentations. So before we go to the award ceremony, we will have 2 more spotlight presentations from Lindong and Ye. Nor, do you want to take it from here?
Lindong, can you share your screen?
Yeah, sure.
Can you hear me well?
Yeah, I can hear you well.
Okay, so
Yes, I can hear you.
Introduce Lindong. So Lindong Kong is a PhD student at the National University of Singapore. His research focuses on robust 3D perception and 3D generation. He has interned in NVIDIA Research, ByteDance AI Lab, OpenNN Lab, and Motional. And the title of his presentation today will be Toward Robust 3D Perception in Challenging Conditions. Lindong, you can start whenever you want.
Thanks, Benoit, for the introduction. Can you see my screen?
Yes.
Okay, perfect. Okay, so my name is Lindong. I'm a PhD student from NUS, and my talk today is about the robustness of 3D perceptions in challenging conditions. So first, a brief introduction of the background. As has been discussed by the other teams before, we are living in a very complex world. So the vehicles must perceive very complex environments, and to in order to make accurate decisions under such scenarios, we will need the models to be robust, to be reliable to those out of distribution scenarios, so that the autonomous driving cars can make correct motions, correct movements, and finally to achieve like full autonomies in this case. So this is our motivation. And in this talk, I will introduce our recent work, Robot 3D, which was accepted to ICCB 2023. So a brief overview of this method. This is the first benchmark for evaluating the robustness of LiDAR-based 3D perception models under corruptions and sensor failures. So this is a bit different from the topic in this competition, because in this competition, we mostly focused on the vision-centric perception models, such as the multi-view camera-based detection, segmentation, and depth estimation. But for this case, we are more focusing on the LiDAR sensors alone, instead of using the images. So in our benchmark, we include 34 different models for both the semantic segmentation and detection tasks. And based on our observations, we drew some in-depth discussions on designing a more robust and reliable 3D perception model. So this is our overview. And this is the taxonomy of different 3D corruptions that occur in the real world. So there are different categories. For example, for the there are fog, wet ground, and snow. These are closely related to the adverse weather conditions. So different from the cameras, the LiDAR sensors suffer in a different way under the adverse weather conditions. For example, there are some of the noisy points in the middle air of around the ego vehicle, and for the wet ground case, the points on the ground, because it can be deflected by the waters on the ground, so this point will be lost. And this is also the case for the snow. And in addition to the adverse weather conditions, we also have the motions disturbances like motion blur. And we also consider the case that certain beams from the LiDAR sensors are missing. And also if there are multiple autonomous vehicles in the same driving scene, then these different LiDAR sensors can interfere with each other. So this is called crosstalk. And so the last two cases is related to the external disturbances like the incomplete echo and cross sensor types. So this is the overview of these 8 different corruption types in our benchmark. And I will show the concrete examples of how we create these different 3D corruptions. So first, this is a clean LiDAR point cloud. We can see from these images that there are some instances like the car, and there are some pedestrians on the road. And this purple areas, this is the drivable surface for this driving thing. Okay, so the first case that we are considering is a fog. So the fog weather can cause backscattering and attenuation of the LiDAR pulse transmission, and this results in the shifts of the range and intensity for the points. So this is how we simulate this case. We can see that by using a physical models to simulate the fog scenario, then some of the LiDAR points in the far regions around the ego vehicle will be deflected to the mid-air near the ego vehicle. So this is the case for the LiDAR sensors under the foggy weather. And another type is for the raining or snowy weather, where there are some waters on the ground, and this kind of water can deflect the laser beams to another directions, so the points will be lost. And this is a concrete examples of how we're simulating this. So we build a physical principled models to simulate this scenario, and then the LiDAR points on the ground will be automatically moved out from the whole point cloud. Okay, so for the snow, this is also a very similar case because the snowflake can reflect the LiDAR points. So there are some of the noises in the middle air of the around the Eagle vehicle. So this is like this. Okay, then next is the motion blur, because this can happen for the vehicle movements or for the movements on the bumpy surfaces and during the U-turning. So this collection circle might not be complete. So there are some certain blurs during this process. So this LiDAR point cloud can be shifted a bit from its original position, and this happens during the local and global levels. Okay, so the next type is beam missing. So for example, there is some of the dust in the air, and this dust can block the laser energies. So this laser points cannot be reflected to the LiDAR sensor. Okay, so to simulate it, we just randomly drop certain LiDAR beams from the whole point cloud, and this becomes to a sparser version of the original point cloud. And for the crosstalk, given that there are several LiDAR sensors in the same driving scene, then this laser pulse can affect each other's. So this will create some of the noisy points in the middle range around the Eagle vehicle, something like this. And for incomplete echo, this is a very special type for the LiDAR because for the cameras, we can see that there are two cars, a black car and a white car. But because the white color can absorb the energies for the laser pulse, so that on the LiDAR point cloud, we can only receive the points from the white car instead of the black car. So this is called incomplete echo. So to simulate this, we just randomly drop the points inside each of the instances in the driving scene to mimic this kind of scenario. And finally, we have the cross-sensor simulations, which means that if we are going to use different types of LiDAR sensors, those LiDAR sensors can be with different numbers of beams, like the 16 beams, 32 beams, 64 beams, etc. And in this case, if we train the models on certain type of LiDARs, and then this model cannot generalize well to the new type of LiDAR sensors. So to simulate this, we just convert a high resolution LiDAR to a low resolution. So this can be done by just drop the certain LiDAR beams from the point cloud. Okay, so these are the 8 different corruption types. And for each type, we include 3 relative levels, easy, moderate, and hard. And given this toolkit, we can simulate different robustness evaluation datasets. So given that we have the LiDAR semantic segmentation and 3D object detection tasks, so we use the semantic kitty, new things, and the Waymo open datasets for doing this. And given that we have the evaluation dataset, then we can do the benchmarking. We can use the existing models that are trained on a clean version of the original datasets, and then they will be tested on our robustness evaluation datasets. And because the LiDAR point clouds is sparse on order, so there are different representation types for different backbones. We also do the benchmarkings for different representations like the range view, bird's eye view, or the 3D representations like the voxels, cylinder voxel, and the cubic voxel. And this involves different operators for processing these different kinds of data. And finally, we define a suitable metric to evaluate the overall robustness of every models that we are going to benchmark. So for segmentation, this is MLU, and for detection, we use the MAP and NDS. And so given this, we can define our robustness matrix. We have two matrices in total. The first is the mean corruption error. This is the error of a certain model divided by the error rate of a baseline model. It mirrors the relative robustness of a candidate model compared to the baseline. And another metric is the mean resilience rate, MR. This mirrors the performance of the model under corruptions divided by its clean performance. So this is the absolute robustness of a models when it's evaluated it's under the clean and the corrupted version of the datasets. Then having the data, the model, the matrix, we can do the benchmarks for different datasets. And here, each of the dots represents a certain models. So the horizontal axis is the task accuracy, the MLU, the MAP, NDS, etc. And the y-axis is the robustness matrix, MCE, MR, and MLU. So we can observe certain patterns from this figure. Some of the patterns are very clear, like there is a linear correlations between the MCE and MLU scores, which means that if the model can perform better under the clean situation, then it will likely to have a higher robustness under the out of distribution scenarios. But this is not true for the mean resilience rate, because on some of the data sets we actually observe a negative correlations of the accuracy and MR. And there are several key observations that we can summarize from our studies, like the use of the representations and under different corruptions. And also we test the use of data augmentations, the voxel size, and some other factors that can affect the robustness of a model. And finally, we show some realization results. Those are the results of different models under the fog and snow corruptions. And also some of the detection results under different corruption types. And so the final topic is about how we can enhance the robustness of these 3D perception models. So the first solution, so when we first make observations of these corruptions, so we can see that this natural corruptions often cause severe occlusion, attenuation, and reflection of the ladder points. So this will cause the variations for the density of a point cloud, which means that most of the corruption types that they will cause incomplete or missing points after this simulation. So given this, we design a density insensitive training framework. So our motivation is to have a two version point cloud. Of the same point cloud, we have two versions. The first is the high resolution version. This is the original point cloud. And second is that we can use a random mask to randomly move out some of the points from this point cloud and create a sparse version of this point cloud. And giving these two inputs, because they are representing the same driving scene, so we can do some optimizations in between them. So we have two branches, the teacher and students. They will extract the features for each of the inputs. And then because they have different number of points, so the length of the features will not be the same. So in this case, for the high resolution version, we just adopt the same mask to get the downsized feature maps. And for the low resolution one, we use interpolations to get the full resolution feature. And then we can calculate the loss in between these two versions. We call the loss completion loss and confirmation loss. So after optimizing the models using this framework, the model can get better robustness under the out of distribution scenarios. So we believe this is a doable strategies to enhance the robustness. And finally, some of our recent works also tries to improve the robustness. For example, in this framework, we design a self-supervised learning methods between the camera view and LiDAR views. And we have tested that the models pre-trained by this framework can have better robustness. Yeah, and another thing is to combine different data sets together to train a single model. And we can see that this combination can often leads to better robustness for the 3D perception models. So this is from our most recent work in CVPR 2024. And that's all for this presentation. Thank you for your attention.
Thank you very much, Ling Dong, for the nice talk. We are a bit out of time, so we still have time for one or two short questions.
Yeah,
Is there
actually,
any question online?
Yeah. So it looks like you goes through your like last two works quickly. So I want to know what is like the key source of like enhancing the robustness like from your last two works. Yeah.
Okay, so from these two works, the first work is about representation learning, which means that we do pre-training first and then fine-tuning the model instead of training the model from scratch. And from previous literature, we know that this kind of study always improves the robustness of certain models because the model can learn something from the representation learning stage. So this is the key insight, and this self-supervised learning strategies also they have been used in our competition by other teams for different tasks.
Impressive. Okay.
And this work is about combining different data sources to train a more powerful models.
Okay.
So instead of using just a single data set doing the benchmarking, and we just combine multiple driving perception datasets together. And we believe that if the model can have a larger training set, then it can learn like more useful features, representations during the training. Then the robustness of this model can be better than training just on a single dataset. So this is the key insight.
Yeah. Thank you very much for your answers. So I'm not very sure I'm right. So I think the key takeaways would be like an appropriate and also diverse and large data sets, and better representation learning, probably through self-supervised learning will lead to robustness in this case.
Yes.
Right. Okay.
Yes.
Okay. Got it. Thank you. Yeah.
Thank you.
Thank you again, Ling Dong. And so we'll move to the next speaker, who is Yi Li. So maybe Yi Li, you can share your presentation.
Wait a moment. I'm showing my screen.
Yi, are you online?
I'm online. Can you hear me?
Yes, please.
Wait a moment. Okay.
Are you sharing your screen? Yi, can you hear me?
Okay, sorry for there is internet interrupt.
Can you share your presentation? I don't see it. Ah, perfect. Thank you so much.
Okay. Okay, can you see
Before
the
you
screen?
start, so let me. Yeah, I see your screen. You need to.
You see screen now?
Yes, we can see your screen.
It's
Okay.
see your screen. It's better now. So maybe let me. You're not in the first slide. And so before you start, maybe a few words about you. So Yi is a master student in robotics at the University of Michigan at Ann Arbor. He has a bachelor degree from Jilin University, and so his research interests include autonomous driving perception and simulation, specifically under challenging conditions such as adverse weather condition. And the title of his talk today will be Optimizing Sensor Placements for Robust Driving Perception. Thank you so much for your talk in advance, Yi.
Okay, thanks for introducing me, and I'm really excited and honored to be here today to talk about the safety of perception in the field of autonomous driving. I'll be presenting my recent work on optimizing sensor placements for robust driving perception. I'm sure everyone here today is an expert in autonomous driving perception, and there's no need for me to keep mentioning the importance of accurate and robust perception for autonomous driving. In RoboDrive Challenge, I'm very impressed by the teams. They have do very, very impressive works through to the robust detection for autonomous driving. So let's take a look at the wide user using dataset, which features 32 beam LiDAR and 6 cameras. These settings were very impressive many years ago, but now it seems they are not enough for the need of high-level autonomous driving. So I want to mention here that high-quality sensing system is also required for accurate perception. Another example is Waymo setup, which uses over 20 different types of sensors and features a quite complex sensing system. I believe specific sensor configurations are Waymo's business secrets, but it's not secret that how to deal with so many sensors is so important to getting high-quality environmental information. So let's see how more autonomous driving companies configure their sensors. The 6 on the left using spinning LiDAR, while on the right, Huawei and NIU use the latest solid-state LiDARs, which are quite impressive for their size. I'm not sure, can you see their size on these slides? You can also find some pictures of their LiDARs on their website. I can dive into each company setup in today, given the limited time. So let's just go ahead to the next point. So now we take a look at how autonomous driving perception systems are developing in the real world. First, we need to deploy sensors on the vehicle to collect data. And then we need to label data to create ground truths. Usually we use many data sets like Kitty or new things which have been completely developed. Finally, we need to train deep learning perception models and deploy the models on the autonomous driving systems. In the past few years, most of the research focused on the right side, that is studying the 3D representation, a novel model architecture, data augmentation, and some training tricks, which involves the work in the computer vision community. But this left side has really achieved less attention from the research community. But this part is really, really important. That's also the focus of our work, because sensor placement. So in our research, we want to ask 2 questions. That is, how does sensor configuration impact the perception abilities of learning-based systems? We might think this the sensor placements have a little or small impact on the perception, but in our experiments show that the impact is quite large and cannot be ignored. The second question is that if there is the impact of sensor placements, how can we improve the robustness of sensor from the sensor placement perspective? So to answer this question, we develop a surrogate metric to represent the feature of sensor placement. This representation is based on the semantic information of real-world scenarios and is independent from deep learning models. To get started with this idea, in this presentation, I will focus on LiDARs only. So we first need to denote a region of interest to further our problem. The region of interest in our work is a 3D cuboid area with an eagle vehicle in the center. For each vehicle in this region of interest, we traverse all the T-frames of samples to compute a probability based on the semantic information. It represents the probability of this voxel being occupied by specific semantic type in all frames. So the denominator is the total number of frames, and the numerator is the number of frames in which this voxel is occupied by a particular semantic category. So for the whole region of interest, we have a probabilistic semantic occupancy degrees. We know in the information theory, we can use channel entropy to describe the uncertainty of a probabilistic event. So we compute the entropy of the probability of each voxel occupied by specific semantic type. Each voxel in this region of interest has an entropy. And next, we can dive into the perception model of LiDARs. We know the spinning LiDARs using beams to detect the environment. When we use different configuration of LiDARs, the beams will traverse different voxels. So we compute the conditional entropy of the voxels traversed by LiDAR beams. For different LiDAR configurations, we can get different conditional entropy. So let's do a short summary to better understand this process. We first define a finite 3D area as a region of interest. Then we generate the semantic occupancy degrees to describe the environment using the semantic information. So using the semantic information, we can compute the probability distribution of the voxels, which is a probabilistic semantic occupancy degrees, let's say the PSOG. And lastly, we devote the surrogate metric of the semantic occupancy degrees. This is the entropy-based metric. We use entropy to describe the uncertainty, indicate the perception capabilities of the sensors. Our hypothesis evaluate the LiDAR placements. We design some experiments. So to find the optimal LiDAR placements, we propose a 4-cycle pipeline, which is called Place3D. If our surrogate metric is correlated to the performance of LiDAR placements, we can find an optimized placement using the surrogate metric without the efforts of testing placements in the real world. To find the optimal LiDAR placements, we also propose a CMA-ES-based optimizing strategy to maximize the metric of MSOG to verify the effectiveness of our optimization. We contribute a multi-condition, multi-LiDAR dataset, and we train several state-of-the-art models and evaluate the performance of baseline. And we're using the optimization method to get an optimized placement. Then we train the model and we compare the performance of the optimized placement with the performance of some baseline LiDAR placements. And to evaluate the robustness of different LiDAR configurations, we use the robust 3D toolkit, which is completely explained by Yaru in the previous slides. So for experiments, we want to validate the efficacy of our method under the problem of optimizing the placements of for LiDARs. We adopt 6 commonly employed heuristic LiDAR placements, which is center, line, pyramid, square, trapezoid, and line row. The line row placement means we change the row angles of the LiDARs in the line placements. The last 2 placements is the optimized placements get obtained from our optimization methods. So now we present the experimental results of our optimization process. We collect LiDAR point cloud data for each LiDAR placement in the color simulator, and we test the efficacy of our optimization strategy using the state-of-the-art detection and segmentation algorithms. The hyperparameters are fixed, and the only change is the LiDAR placement. We can see this picture first. The horizontal axis represents the scores for various surrogate metrics, while the vertical axis indicates the performance of the object detection and the semantic tasks. The curve of the different colors represent various deep learning methods, and the MSOG scores for different placements are displayed in this table. We compute the MSOG scores of different placements. Here you can see that the optimized placement using our optimization methods get the most large MSOG scores. The large MSOG scores means it's close to the 0 point because our metric is the representation of the minus of the entropy. So the entropy is more, and the metric scores of our goes up. So we can go back. So let's go back to this figure. Metric scores goes up. The performance of the performance of detection will goes up. This is a very evident way. Even if there are some fluctuations in this figure, but the rising trend is very evidently to see. And this figure is the result of the semantic segmentation. Both these results are evaluated on the clean data. So let's move to the robustness evaluation. We utilize the robust 3D toolkit to generate corruption for robust evaluation, and we report the average performance on the different types of corruptions for both tasks. The first figure illustrates the performance on detection, and the second figure illustrates the performance on segmentation. Although the correlation between the surrogate metric of the performance is not as pronounced as with the clean data in the last slides, our optimized placement still achieves the best performance, surpassing all the other placements. So let's make a conclusion of this representation. We introduce a surrogate metric of the semantic occupancy grids to evaluate the light placement quality, and leveraging the MSOG metric, we propose a novel optimizing strategy to refine market data placements. Our future work will focus on investigating the impact of sensor configuration for more types of sensors and delving into the gap between simulation and the real world. And thanks for my collaborators from Carnegie Mellon University and the National University of Singapore. You can scan this QR code to get our archive paper. So thank you for listening.
Yeah, any questions from the audience?
I sort of lose the connection. Are you done with your talk? Thank you so much. We have time for 1 or 2 questions.
Okay.
Okay, I guess if there are no questions, we'll have our coffee break. It's a very short coffee break. We'll come back at 4:30. Then we'll have our award ceremony. Yeah. Thank you, yeah, for your presentation. Thank you.
Okay.
Okay, great. See you soon.
Hello, everyone. Welcome back. We're moving on to the next section, which is the award ceremony. Okay, so we will first present, announce the winning solutions for track 1, robust bird's eye view detection. So the third place in track 1 will be Cyber BV. So their performance is 49% on the phase 2 of the leaderboard, which is nearly 26.2% improvements over the baseline BEV former. So congratulations to the team Cyber BV. This is the certificate for our winners, and you are the third place. Based on that, we have the second place, which is Ponyville Autonauts Ltd. So they have a even better model which can achieve over 50% NDS on the phase 2 leaderboard. And congratulations to the team from Ponyville Autonauts Ltd. So this is the second place for our track 1. And finally, we will announce the champions for track 1, which is Deep Vision. They achieved 52.1 NDS on the leaderboard of track 1, which is nearly 30% improvements over the baseline model. So this is a very huge achievement for this team. And congratulations to the team members, Xu Cao, Hao Lu, and In Cong Chen. Okay, so this is the 3 winning solutions for track 1 of the RoboDrive challenge. Let's move on to the next track, which is robust map segmentation. So the third place for this track will be the Samsung Research. So their solutions achieved 29.8% MLU scores on the phase 2 leaderboard of this track. So congratulations for the Samsung Research China Advanced Research Lab. And for the second place, this goes to Crazy Friday. So Crazy Friday had a around 5% MLU compared to the third place, and which is nearly 20% improvements over the baseline B-verse. So the second place goes to the team Crazy Friday. And so for the first place, they have the team members of this team have made very notable achievements on this track. They achieved 48.8% MLU scores on the phase 2 leaderboard of track 2. And this goes to the team Safe Drive SSR. So congratulations for Xinliang Huang and Yu Tian from the Safe Drive SSR. You are the champions for track 2 robust map segmentation of this challenge. Congratulations again. Okay, so let's move on to the third track, which is robust occupancy predictions. Again, we have 3 winners for this track. So the third place goes to the HM Unilab. So although the improvements is just 0.2%, but this track is very challenging because the estimating the semantic occupancies from images is a very challenging task, and under the different corruption types is even challenging. So this gives the third place to HM Unilab. And for the second place, the team APAC Blue, they improved the baseline for 1.6% MLUs on the phase 2 leaderboards. And so the second place gives to APAC Blue. Okay, again, so our winners for this track, again, they have made a very notable achievements. They achieved 22.3% MOUs on the phase 2 leaderboard of track 3. So this is a huge improvement compared to the baselines around the OCC. So the first place goes to the team Viewformer. So congratulations for Jinke Li, Xiao He, and Xiaoqing Chen from Viewformer team. So congratulations for winning the champions for the track 3 robust occupancy predictions in the RoboDrive challenge. Okay, let's move on to track 4 robust death estimations. So the third place, so first, the metric for this track is different. It's the error rate. So it's the lower, the better. So the baseline surround death has a error rate of 30.4%. And the team CUSTZS, they have achieved a huge improvement over the baseline. So congratulations to the CUSTZS team for winning the third place in this track. And the second place goes to BUAA Trends. This team's solution achieved 20.5 error rates on the phase 2 of this track. So congratulations to all the team members from BUAA Trends. Finally, we have our champions for track 4. Which is HIT-AIIA. Their methods achieved the lowest error rates on this leaderboard, so which is 18.7. So congratulations for Jian Liu, Yifan Mao, Ming Li, Zihan Qing, Jiayang Liu, Jialei Xu, Cun Xichu, Wen Bozhao, Jun Jiang, and Xianming Liu from the HIT-AIIA team. So you are the champions for track 4 robust death estimations in the RoboDrive challenge. So here comes to the last track in our competition, which is track 5 robust multimodal bird's eye view detection. So the third place goes to HIT-SDE RoboDrive team. So their multimodal BV solutions achieved 46.6 NDS on the phase 2 of this track. So congratulations for the HIT-SDE RoboDrive team for winning the third place in this track. As for the second place, this goes to the Ponyville Autonomous Ltd again. They're also the second place for the track 1 in this challenge. So in track 5, they achieved 48.2 NDS on the phase 2 leaderboard. So congratulations again for the team members from Ponyville Autonomous Ltd. And here comes to our final champions, which is the champion of track 5, Safe Drive Pro Max. Their model achieved the highest NDS scores on the phase 2 leaderboard of this challenge, of this track, which is 49.7. So this is almost 10.6 NDS higher than the baseline BV Fusion, and which is a very huge achievement for this team. So congratulations for Xiaoyang, Haichen, and Li Hongwang for winning the champions for the track 5 of this RoboDrive challenge. Okay, so these are the winners for this challenge, and we're going to introduce our innovative solutions in this competition. So the innovative solution honorable mention goes to the Samsung Research China Advanced Research Lab team from track 2, robust map segmentation. So the key innovations of their solutions is that this team implemented a temporal fusion module that integrates data across multiple frames, along with a strong backbone and effective data augmentation techniques. So congratulations to the team, Samsung Research for winning the innovative solution honorable mentions in this competition. And we have another honorable mention award, which is for the BUAA Trends team from track 4, robust depth estimation. So the team introduced the fusing features across skills depth estimation, which is FFAS depth framework with a multi-branch network architectures and advanced data augmentations. So congratulations again for BUAA Trends for winning this honorable mentions of Innovative Solution Award. And finally, the Innovative Solution Award goes to Viewformer from track 3, robust occupancy prediction. So the key innovation includes introduce the Viewformer framework to encourage spatial interactions through view attention, as well as a streaming temporal attention module and a reverse video playback mechanism. So their methods also achieved the first place on track 3 of this challenge. And another innovative solution gives to SafeDrive Pro Max from track 5, robust multimodal BEV detection. So this team developed the against sensor failure ASF model with designs on self-supervised feature reconstruction, image feature enhancement for LiDAR, and a robust fusion and decoding strategy. And again, their methods achieved the first place on track 5 of this challenge. So congratulations to the SafeDrive Pro Max team. Okay, so these are all the results and from our competition this year. So I would like to make some concluding remark to wrap back all the details of this workshop. Okay, so this workshop is for the 2024 RoboDrive Challenge, which is held on the ICRA 2024. And this workshop is for robust autonomous driving perceptions under out-of-distribution scenarios. And we have received huge attentions across the academia and the industry. So to further contribute to our community, we make the following resources publicly available to everyone so that they can access our materials. The first is these video recordings. It can be downloaded from our website. And we also summarize the key innovations of each of the top performing solutions into a single technical report, which can be downloaded from this link. And our benchmark toolkit will be is publicly available to on GitHub. So if you want to use our toolkit to develop your models and your other methods, then feel free to use it. So this is the technical report of this challenge. And we will also post all the reports from every team on our website. So if you are interested in a specific solutions from these teams, then please visit our website and download their reports. And finally, we acknowledge the use of some of the previous work developed by our collaborators, which is the Robot BV, Robot Depths, and Robot 3D benchmarks. So if you are interested in this kind of research, then feel free to read our papers and use our code. Okay, so thanks everyone again for making the contributions towards this challenge, and hope we can see you again next year.
Thank you, everyone. Thank you.